All right. So let me show you some properties of Laplace transforms. These are the transforms of certain sample functions. First thing is, the first property is that it is linear. So suppose you had to do 3 cosine 2t minus 5t, and you had to take the Laplace transform of that. What do you do? Well, first, it's linear, so any constant multiple can be brought outside. So, and minus can be split. So you end up with Laplace transform of cosine 2t multiplied by 3 minus 5 times Laplace transform of t. What's that? Cosine 2t is here. Cosine 2t is here. With a being 2, is s over s squared plus 2 squared. So it's s over s squared plus 4 minus 5 times, for t, that's t to the first power, so it's 1 factorial over s squared. 1 factorial is 1, so it's 1 over s squared. So the result is that it's 3s over s squared plus 4 minus 5 over s squared. And that kind of property is called linearity. Okay? Laplace transform is linear. Another important property is that there's a shifting property. So let's say you know that Laplace transform of a function of t gives you another function of s. Keep in mind that this lowercase f function and capital F function will look completely different. Right? So in this, if you look at this, it's like this is small ft, that's a capital Fs. It's a function of s, this is a function of t. Let's say you're given this. Okay? Then there's a nice formula that says if you were to do e to the at times f of t, you will get capital F of s minus a. That's the shifting formula. Let me give you a quick proof for it. Okay. Now, this is the assumption, right? What does this mean? This implies that your capital F of s is the integral from 0 to infinity of e to the negative st of ft. Now, given this fact, we want to know what's the Laplace transform of this. And I claim it's equal to this. So let's see why this is true. So first, Laplace transform of e to the at ft. If I just simply write down the formula for Laplace transform of this thing, it's 0 to infinity of e to the negative st of e to the at times f of t dt. Isn't that right? It's all I do is take any function here, replace it right here. Okay, that's what Laplace transform means. And then if you look at this, it's 0 to infinity. This is e to the at minus st ft dt. Because if you have same base, the exponents add up. And then you can further rewrite this and say 0 to infinity of e to the negative s minus a t f of t dt. Okay. And then, just to see that these two are the same, just check what you get if you multiply the minus. If you multiply negative times s times t, you get negative st just like here. If you multiply negative times negative a times t, you get positive at just like here. Okay? So we see that this is equal to this. Now, at first, it seems strange what this will, what the given has anything to do with our final result there, but it has everything to do with it because look what this is saying. It's saying that if you have f of something, then it's 0 to infinity of e to the negative of something times t f of t dt. You see that? I mean, f being a function of s means whatever you plug in here, you can compute it by plugging that in here. That's what this result is saying. Is that good? And then I want to put s minus a here. Then what should I put here? S minus a, the same thing, right? But look, what is this? That's exactly the same as this one, right? Okay. Which is exactly same as this, which is same as this, which is same as that. Okay? Therefore, I've shown that this is true. Okay. Now, once you know that, then it kind of makes sense why we have this formula and that formula. So let's see how this shifting formula explains this one, for example. Okay, so first, take the above, L of sine AT, and replace A by K. You can do that, right? If this is K, this should be replaced by K, and that should also be replaced by K. So we know that L of sine KT is K over S squared plus K squared. Now let's see what happens if I put e to the AT to it. If I put e to the AT here, what does this formula say? I have to replace s by s minus a. That's what it's saying, right? Okay. So let's see what that says. Here, Laplace of sine of kt equals to k over s squared plus k squared. And we're treating this one like f of t and this one like capital F of s. And then we know that Laplace transform of e to the at sine kt is f of s minus a, where fs is this thing, right? So let's take this. F of s is k over s squared plus k squared. From this, we know that f of something is k over something squared plus k squared. And finally, what is f of s minus a? What do you do? We replace this blank by s minus a. Okay? And therefore, we know that this fs minus a is indeed k over s minus a squared plus k squared. So that's where this shifting formula is being used here. Okay? So you could indeed do the calculation. It's a very, very tough calculation. Or you can just say, oh, I know this, and let's apply the shifting formula, and we are done. Okay? So that's another way to figure out this. Okay. This one, for example, can be thought as the following. What's the Laplace transform of 1? Do you remember? It's this one, right? With t n being? If n is 0, then you get Laplace transform of 1. What's 0 factorial? 1. 1. 1 over s is the first power because n is 0. So we know that L of 1 is 1 over s. Now what do you get if you had e to the at times 1? Then it's this shifting formula, right? So I have to replace s by what? S minus a. Done. That's why you get this. Okay? So that's how the shifting formula is.